So we have talked about lines. Now we're going to talk about planes. Just to point out, we're talking about planes in R3. It's important that we are actually in 3 dimensions to be able to identify planes of a line. Now, to begin, we can give ourselves what we would call, again, like a vectorial equation of a plane. So in this equation, essentially what we're doing is taking two lines and extending them infinitely for us to be able to then make a space around them, and that space becomes this like flat plane. One thing that's important is that both of these vectors, v and w, that we use to generate this plane is that they have to be non-parallel. If they're parallel, then we actually aren't able to generate a plane. So if I was to draw this, so I've got this plane here, and using the information that I have, we're going to have this point P, just like we see in the equation. Now from P though, we're going to take two vectors. We're going to take a vector v, and we're going to take a vector w. And so P, again, is still called our support point, but u and v, not u and v, v and w are generators of our plane phi. We're identifying planes with the Greek numeric phi. So let's see what this does. So construct the vectorial equation for a plane going through points A, B, and C. Well, if I look here and I've got these 3 points A, B, and C, what I really need to do is use A, B, and C to construct two non-parallel vectors. Okay, so let's start there. Why don't we just go AB? All right, AB will be 0, 2 minus 1, 1, 2 minus -2 is 4. And then I'm going to also construct AC, which is -2, 0, and +2. So now I can tell right away that these two vectors are not parallel. And one of the ways I can tell that they're not parallel is in fact where the components equal 0. So because I've got a 0 in the first component, there's nothing I could multiply it by to get -2s, and that's how we can show that something's parallel, is by showing that they're scalar multiples of each other. So they're not parallel, so these will become my generators of my plane phi. Now, all I need to do then, when I write out the vectorial equation of phi, is pick any of the points. And it doesn't matter which point I pick, because any of these points could be a support point because I've said they're all on the plane. It also doesn't matter which order I actually state the generator vectors in. But it is really essential that we make sure that we identify T and S as real numbers. So here, just to make note, we could choose A, B, or C, and we could use any two non-zero, non-parallel vectors with endpoints A or B. So that's the other thing. When I formed A and B, I could have actually formed BA and CA, and those two would have also been generators. So there's more than one way to actually accomplish this problem. And what we would actually find is that we would get a vectorial equation for the plane that looked different, but it would actually be equivalent to it. So again, I'm emphasizing that this is the vectorial equation of a plane because I'm going to introduce now a different equation for the plane, which might become more common to use and help us solve our problems. But before we actually define a different equation, we need to define what we call the normal vector. So the normal vector to phi is any vector n that is orthogonal to P1, P2, which are a pair of points on the plane. Or essentially, the normal vector phi is orthogonal to the plane. So if I have a plane and I've got point P1, another point P2 here, what's going on is my normal vector will be a vector that is orthogonal to my plane. So thinking of our planes as a flat piece of paper, it comes straight up from there. Now, the thing is that considering that planes themselves are infinite, any plane has an infinite amount of normal vectors. And so we just need to make sure that our normal vector holds the condition that it's perpendicular or orthogonal to our plane. Now, if we remember, when we take our cross product, so just a reminder, cross product is a vector orthogonal to both v and w. And so if I've got two vectors, v and w, that are generators of my plane, I could actually find the normal by just taking the cross product of them. And that's what this tells me. It says that if I let q be any point and let my equation of the plane be identified with phi, then with point x naught, y naught, z naught, and n, then my normal vector, I actually end up with this equation of a plane. What it is I use the normal, a, b, and c, the values of the normal, and it's written ax plus by plus cz, and d is found by plugging in any point into the plane. And this is called the Cartesian equation of phi. Now, the Cartesian equation of phi will more likely be used in some situations. Now, we're asked to prove how this can be equivalent to the vectorial equation. So if q is on phi, because we say let q be any point, so if q is on phi, then the vector pq dot n equals 0. Okay. So x minus x naught, y minus y naught, z minus z naught, dot a, b, c equals 0. That's what we're saying. We take the x minus x naught, y minus y naught, z minus z naught as the vector, how we find vector pq. So now if I'm going to actually do the dot product here, that would give me a times x minus x naught plus b times y minus y naught plus c times z minus z naught still equals 0. Well, I'm going to now distribute this in. So I'll have ax minus ax naught plus by minus by naught plus cz minus cz naught equals 0. But I'm going to collect all the positive values, and I'm going to take all the negative values to the other side. by naught plus cz naught. And thus, from this equation, we can say that ax naught plus by naught plus cz naught is equal to d, and ax plus by plus cz equals ax naught plus by naught plus cz naught is the Cartesian equation of phi. Now, with that information though, we can go on and say that if we do know that ax plus by plus cz equals ax naught plus by naught plus cz naught is the Cartesian equation of phi, then let Q be equal to x1, y1, z1 be any point that satisfies the above equation. So we're saying we already know that Q is on the plane, so Q is actually any point then that satisfies the equation. And hence, ax1 plus by1 plus cz1 equals ax naught plus by naught plus cz naught could be rewritten as a x1 minus x naught plus b y1 minus y naught plus c z1 minus z naught, which could also be rewritten as a b c dot product with x1 minus x naught, y1 minus y naught, z1 minus z naught equals 0 in both of these cases, and thus we've now shown again that ABC is orthogonal to PQ, so Q is on phi. And there we have it. So let's look at a quick example here. We're asked to give the Cartesian equation of the plane through points A, B, and C here. Now, you'll notice that A, B, and C here are the same as in the previous example we looked at. So there's a couple of things. We already know AB is 0, 1, 4. And we know that AC is -2, 0, 2. Now, it was from here that we wrote out the vectorial equation, but what we want to do now is actually take the cross product. Because, as we reminded ourselves on the previous page, the cross product is orthogonal to both the vectors that we take the cross product of. So that's 2, and then I've got -8 minus 0, and then I've got 0 minus -2, which will give me +2. And that's my cross product right there. So thus, I'm left with 2x plus, well, I'll just jump to -8y plus 2z equals d. Now to find d, D, plug in any point that is on the plane. Okay, so I'm actually going to plug in point C, just to change it up and not always choose A. So this gives me -2 minus 8, which gives me -10. And so thus, 2x minus 8y plus 2z equals -10 is the Cartesian equation of phi with points A, B, and C on it.